All right, thank you, Veronica. I'm excited to be here. I work in a field called quantum information science. Now, three of the great themes of 20th century science were quantum theory, computer science, and information theory, all of which have had a huge impact on our everyday lives. And quantum information science is a kind of synthesis of these themes, which we think is laying the foundation for revolutionary technologies of the future, and also giving us new insights into nature. Now, I'd like to reiterate a point that Veronica was making. You know, we sometimes worry that as science advances, it splinters into more and more specialized subfields. And that's a legitimate thing to worry about. But there's a countervailing tendency, which is as our knowledge deepens, we find new ways of connecting together different fields of science, and sometimes in unexpected ways. Early in my career, I worked on particle physics and cosmology, and you might think those are very different fields because particle physics is the science of very small things and cosmology very large things, but they're actually closely connected. For example, if we want to understand what happened very early in the evolution of the universe when it was very hot, we need to understand collisions of elementary particles at very high energy. So from cosmology, we can learn things about particle physics and also vice versa. And now what I think quantum information science is about is we're in the early stages of the exploration of a new frontier of the physical sciences. Sometimes I call it the entanglement frontier for reasons we'll see, or the complexity frontier. And as usual, progress is driven both by new tools and by new ideas. As far as tools go, we're now developing and perfecting the laboratory tools to create and precisely control very complex systems of many particles interacting quantum mechanically, what we call highly entangled systems. And these systems are so complex that we can't simulate them with our most powerful digital computers or understand their behavior very well using existing theoretical ideas, and that opens new opportunities for discovery. And as we'll be seeing throughout the day, the ideas about how to understand these complex quantum systems connect with a variety of areas of physics, including trying to understand space-time itself. Now, our conviction that this new frontier is going to be fulfilling to explore rests to a large degree on certain phenomena that occur in quantum physics, particularly when many particles are interacting, which goes under the buzzword entanglement. And this is the word that we use for the correlations among parts of a quantum system, which are very different from the correlations we normally encounter. And so this is the basis of what we sometimes refer to as the weirdness of quantum theory. And the weirdness is fun to think about, but we're also learning ways to put that weirdness to work, both in technology and in advancing our understanding of nature. So I want to give you some ideas about how quantum physics is different from ordinary phenomena. And we'll start with this example. This is a game that I'm sure you're familiar with, the shell game. There are 3 cups, and we're assured that there's one ball which is under one of the 3 cups, and you don't know which. And I might try to deceive you about where the ball is, and then it's your job to decide which cup to lift and to see if the ball is revealed, and if it's there, then you win the game. So in this case, it was under cup number 1. And if you ever doubt that there's really just one ball, and exactly one ball under the 3 cups, in a round of the game, you're entitled to challenge me, and then I'll lift up all 3 cups, and you can see that there really is a ball under one of them. Of course, that round of the game doesn't count, and nobody wins. So now I'd like to consider a version of the game where the rules are a little bit different, where there's a gorilla who is kept off stage in a soundproof booth when you decide which cup you want to lift up, and he doesn't know which cup or what you found under that cup. Now you might ask, why is it a gorilla? This is actually me wearing my gorilla mask. And so I'll tell you one of my secrets of teaching. It sometimes happens that I'm scheduled to give a lecture on Halloween. And it's become my habit that when that happens, I come to class dressed as a gorilla. And I do this whole shtick where I say, well, John couldn't be here today, so he thought you might want to hear a lecture by a gorilla. And so it goes on like that. And the students say, John, why did you give the class dressed as a gorilla? And I'll say, well, 10 years from now, 20 years from now, you're not going to remember much about this class, but you're going to remember the day I came as a gorilla. And this really works. Sometimes students come back 20 years later and they say, you're right, I remember the gorilla. Well, anyway, in this version of the game, after you've already looked under the cup and the gorilla doesn't know what happened, the gorilla comes into the room and he does something with the cups, or we're not quite sure what he does, and then he decides either to give thumbs up or thumbs down. And when he gives thumbs up, that means it's an official round of the game. It counts. When he gives thumbs down, then that round doesn't count. Okay? And what we find when we play this gorilla version of the game many times is it's observed that in the rounds when the gorilla gives thumbs up and you have looked under cup number 1, every time you found the ball under cup number 1. Okay? And so now we could ask the question, when the gorilla gives thumbs up and you looked under cup number 2, is the ball there or not? Will the ball be there always, never, or sometimes? So remember, when he gives thumbs up and you looked under cup number 1, it was always there. So the question is, when he gives thumbs up and you look under cup number 2, is the ball going to be there always, never, or sometimes? So what do you think? Who would say always? Never? Sometimes? Well, a lot of people are for sometimes. Well, of course, the answer is never. Because the ball is under cup number 1 every time. How could it possibly be under cup number 2? Because there's just one ball, right? Question.
Question. Does the gorilla say it before you do the looking or after?
He does it after.
Okay.
Yeah. Okay. So now, of course, there's a quantum version of the game with the quantum gorilla. And it turns out these are really quantum balls and cups. And the gorilla knows this, and so he's able to do things that a quantum physicist can do to the balls and the cups. And same thing as before, every time he gives thumbs up, we find that if you had looked under cup number 1, the ball was always there. So in the quantum version of the game, what do you think? When he gives thumbs up and you looked under cup number 2, was the ball there always, never, or sometimes? How do you guys are so good? So a lot of you think it's always. That's right. It turns out, even though there's just one ball, and remember, if you ever doubt it, you can challenge, and then all 3 cups reveal that there's just one ball there. There really is just one ball. And yet, when he gives thumbs up, when you looked under cup number 1, the ball was always there, and when you looked under cup number 2, the ball was always there. So how is this possible when there's only one ball? Well, the secret of the quantum gorilla is he has a way of looking at the cups and the balls that we wouldn't be able to do if they were ordinary classical cups and balls. He makes a kind of collective observation on the 3 cups. And let's go under the hood a little bit and see how that could possibly work. So in quantum theory, I can think of the 3 possibilities for where the ball is, cup 1, cup 2, cup 3, as 3 distinguishable states. But in quantum theory, we're allowed to regard those states as basis vectors in a vector space in 3 dimensions. And these are 3 orthogonal directions in that space, which are perfectly distinguishable from one another. So it turns out what the gorilla is doing is, when he comes into the room, he tries to take the vector and project it onto this different vector. So this is just a uniform sum of the 3 possibilities in which they all occur in a symmetric way. So the ball has equal chance of being under cup 1, cup 2, or cup 3. But he tries to project the state by making a certain kind of measurement on to this different direction, a different combination of the three basis vectors in this three-dimensional space. So what happens is if you were to look under cup number 1 and the ball is not there, then you know for sure that the ball is not there, so it has to be under one of the other two cups, and now it's going to be a uniform superposition, as we say, of the other two possibilities, cup 2 or cup 3. And likewise, if you look under cup number 2 and the ball is not there, now it's going to become equally likely that it's cup 1 or cup 3, and so it becomes this vector which is a combination of those two basis vectors. And so the key thing is that when you don't see the ball under cup number 1, this vector is orthogonal in this three-dimensional space to this one. We can just calculate the dot product of the two, and we know E2 dot E2, their unit vectors, is going to be 1, and so is E3 dot E3, but there's minus sign. So they're pointing in orthogonal directions. And that means that if the ball wasn't under cup number 1, the gorilla would never be able to do a thumbs up, and same thing if it's not under cup number 2. So that's how it works. There are quantum rules for calculating these things, and when you know the rules, you can easily see how it works. But they're very different from the rules that govern real baseballs and cups. So that was just kind of a parlor trick to get you interested. Now I want to talk about something that's a little deeper. So I have this friend, Donald. He lives in Denver. I call him Donald from Denver. And he has this company that manufactures coins, and you can buy from Donald a box, and it's got 3 coins in it. And like any coin, it can come up either heads or tails. But when you open the box, these coins are covered up so you can't see whether they're heads or tails. Now, when you open the box, now you get to decide which of the 3 coins, which are conveniently labeled 1, 2, 3, you're going to uncover to see whether it's heads or tails, okay? And when you do that, these boxes are rigged up in such a way that you can choose to uncover coin number 1. In this case, you see that it's heads, but then poof, coins 2 and 3 disappear. You never get a chance to uncover those coins and see whether it's heads or tails, try though you might. So remember, it's up to you to decide which of the 3 you're going to uncover. In this case, I decided to uncover coin number 2, and it turned up tails, but 1 and 3 disappear. They're gone, and I'll never know what I would have found if I had uncovered them instead. Now, I have these friends, 2 physicists, Alice, who works at Caltech, where I'm from, and Bob, who's right here at UCSB, and they know Donald. And for years now, Donald has been making pairs of these coin boxes and sending one member of the pair to Alice in Pasadena and the other to Bob in Santa Barbara. And he's done this millions of times. So there are millions of these matched boxes, and we know how they're paired up. And Alice and Bob have been doing experiments with them, uncovering the coins to see whether they're heads or tails. And they found some interesting things about these coin sets. For one thing, Alice finds that when she uncovers one of the coins, it doesn't matter which one, 1, 2, or 3, the probability is 1/2 of finding heads and 1/2 of finding tails. And she's very confident about that because she's done millions and millions of trials, and about half are heads and about half are tails. And that's true for all 3 possibilities, any one of the coins she can uncover. And it's the same thing on Bob's side. Okay? And they're quite confident of that because they've done so many experiments to test it. And there's another interesting thing. When Donald sends these boxes, these paired boxes, to Pasadena and Santa Barbara, they're correlated in an interesting way. Because when Alice and Bob both uncover the same coin, they always see the same thing. So, for example, in this case, Alice uncovered coin number 1 in Pasadena. Bob, the same coin, uncovered in Santa Barbara. And they could have seen heads or tails. The probability of each is 1/2. But in fact, they both saw tails. Okay? And this time, they decided to uncover coin number 2 in Pasadena and Santa Barbara. They could have found heads or tails, about equally likely. In this case, they found heads. They both found heads. And in fact, they know because they've tested it millions of times, this is how it always works. If they both uncover the same coin, they're always going to see the same result. Could be heads, could be tails, but always the same if they uncover the same coin. So there's no doubt about that anymore. Now, one day, I guess I'm going to do it one more time. There we go. We uncovered coin number 2, this time in both places, and could have been heads or tails. This time it was tails, and they both found tails when they uncovered the same coin. Let's see, do I have another one here? No, okay. Now, one day Alice and Bob are talking on the phone. They talk on the phone a lot because they want to compare their results. And Alice is saying, you know, Bob, sometimes I just get so frustrated because I wish I could uncover 2 of my coins and see for both of them whether it's heads or tails, but I can never do it because every time I uncover one of the coins, the other 2 poof are gone, and I never get to find out what I would have found if I had uncovered that coin instead. There's just no way to do it. I've tried, and I can't. And Bob thinks for a minute, and he said, wait a minute, Alice, you're wrong. There's a way to uncover both of the coins. Look, suppose you uncover coin number 2 in Pasadena, okay? Well, what if I uncover coin number 1 in Santa Barbara? Now, we know for sure that when I uncover coin number 1, if you uncovered coin number 1, you're sure to find the same thing that I found. No doubt about that, because we've tested it time after time, and it always works. So this time, I can uncover coin number 2, you can uncover coin number 1, and we'll know for sure, without any doubt, what you would have found if you had been able to uncover both coin number 1 and coin number 2 in your lab in Pasadena. Makes sense, right? And Alice says, well, maybe so, Bob, but you know, I'm not quite sure. I sort of have nagging doubts because we'll never really know for sure in this particular case what I would have found if I had uncovered coin number 2 when you uncovered coin number 2, because I didn't. I uncovered coin number 1 instead, right? And there's no way you can ever uncover 2 of the coins. And Bob says, Alice, you're being so stubborn. I mean, look, I'm in Santa Barbara, you're in Pasadena, we're a couple hundred miles, well, over 100 miles apart from one another. You certainly don't believe that anything I do in Santa Barbara is going to have any influence on what you find in your lab in Pasadena. That's not how it works. That would be absurd. What's happening is Donald is sending us these correlated sets of coins. And so we don't know until you uncover them for each coin whether it's going to be heads or tails, but we know they're perfectly correlated. And so it's just that I'm finding out information about what's happening with your coins. When I uncover my coin number 2, that's enough to tell me what you'll find, so I can go ahead and uncover coin number 1. But Alice still has doubts, and she said, well, I'm not sure. Maybe we should do an experiment, see what happens when we uncover different coins. And Bob scoffs, you know, he said, well, they'll never fund it. It's such a dopey experiment. I mean, who's going to care? And Alice said, well, I heard about this theorist. Bob and Alice are both very skeptical of theory. But there's this theorist, his name is Bell. He lives far away, and I hear he thinks a lot about coins. So maybe we should talk to him. And if he makes some kind of prediction about what we'll find when we do the experiment, then we can test his prediction. And that'll make the experiment more interesting. And Bob says, yeah, and it won't matter if his theory is really dopey. We can still test it and, you know, show that it's wrong. And so they go and they talk to this guy, Bell. It's a long trip. They have to go to Switzerland. And they explain to him all about the coins. I guess this explains what I was just telling you, how we uncover 1 and 2. Bob uncovers coin number 2, so we know what Alice would have found. And this time, you get the idea. Bob uncovered 3, so we know what Alice would have found if she'd uncovered 3, but she uncovers 2 instead. Okay. So they're talking to this guy, Bell, and they explain how the coins work. And Bell thinks for a long time, and he says, okay, I think I understand what you're saying. These coins are perfectly correlated. So the reason we only have probability 1/2 of seeing heads or tails is we don't know exactly what's under those black covers, but something's under the black covers. It's just that we're ignorant about what it is. And so we use probabilities to describe that, to encode that ignorance. But one thing we know for sure is that they're always perfectly correlated when you uncover the same coin. So we might as well think of a probability distribution that applies to whether you get heads or tails for each one of the 3 coins in Alice's laboratory, because Bob's laboratory, we're going to see exactly the same thing when we uncover the same coin, okay? So that means there are really 8 possibilities. You can see either heads or tails when Alice uncovers her coins in Pasadena for coins 1, 2, and 3. And one thing we know about probabilities is that they're non-negative and they have to sum to 1, right? And so Bell goes on and he says, well, look, I can tell you what the probability is if you uncover coins 1 and 2. The way you do it is Bob uncovers 2 in Santa Barbara and Alice uncovers 1 in Pasadena, because I just have to sum up the probabilities for all the cases where you see the same, either both heads or both tails, in when you uncover coins 1 and coin 2. In other words, let me ask the question, what's the probability that you see the same thing when we uncover different coins? And there are 4 possibilities for the 3 coins where 1 and 2 both give the same thing. Could be heads, 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 tails, 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 heads, or tails, 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 right? In both cases, it's either heads, heads, or tails, tails for coins 1 and 2. And we can do the same thing for coins 2 and 3 and coins 1 and 3. Similar formula for the probability that you see the same thing. And Bell goes on and he says, well, look, there's something interesting to say here. Because what if we sum these up, the probability that you see the same, either both heads or both tails, for coins 1 and 2, or for coins 2 and 3, or for coins 1 and 3. When we add them up, all the possibilities occur, all 8 possibilities, and 2 of them occur 3 times. The heads, 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 and tails, tails, tails contributes to finding the same thing for any one of the pairs of 3 coins. And so when you sum it all up, you're summing all the possibilities, and that's going to give 1, plus these extra probabilities, which are surely non-negative. So one thing we can say for sure is that the probability of seeing the same thing when you look at coins 1 and 2, plus the probability for coins 2 and 3, plus the probability for coins 1 and 3, has to be greater than or equal to 1. And Bell says triumphantly, that's it. That's my inequality. Okay? And Bob says, okay, I guess the math looks right, but I don't really get what's going on. Why does it work? And Alice says, you know, I think I see. If you were able to uncover all 3 of the coins, then at least 2 of them would have to be the same, right? Because there are only 2 possibilities and there are 3 coins. And Alice says, Bell, isn't that what it is? And Bell strokes his chin and stares into space for a long time, and finally he says, yes. So there's a simple explanation for this inequality. And so now they're ready to do the experiment, and they're delighted to find that Bell is that rare beast, a theorist they can understand. They know what they're supposed to do. And so they do the experiment, and of course they have to do it millions of times to get these probabilities estimated with very good statistical accuracy. And when they do that, they find that the probability, this is what Bell said, should be satisfied, but they actually find that when they uncover coins 1 and 2, the probability of seeing the same thing, either heads, heads, or tails, tails, is 1/4. And the same thing when they uncover coins 2 and 3 and coins 1 and 3. And if I'm doing the math right, the sum of 1/4 plus 1/4 plus 1/4 is not greater than or equal to 1. So something went wrong. This Bell's inequality, which seemed to follow from unassailable reasoning, failed in the laboratory. So how could Bell have been wrong? He seemed to make an innocent assumption, which was that the probabilities that govern these coins reflect, as probabilities normally do, our ignorance about the situation. Each coin is really heads or tails, it's just that they're covered up so we don't know which. And the correlations are telling us that Bob's coins are correlated with Alice's, but still the probabilities are governing the things that we don't know about the full state of the coins in the boxes that Donald is preparing. And he also made the innocent assumption that something that Bob does in his laboratory in Santa Barbara can't possibly affect anything that Alice is going to see far away in Pasadena. So what are we learning from the failure of Bell's inequality? Well, one way of saying it is this. We shouldn't talk in the quantum world about counterfactuals, about things that we might have done but didn't actually do. In this case, our reasoning was based on the idea that after Bob uncovers coin number 2, if Alice had made the measurement on coin number 2, if she had uncovered that one, we know what she would have found, but she didn't. She uncovered coin number 1 instead. And so what we're learning is that a measurement that you don't do doesn't have an outcome. It isn't right to say that the uncovering of coin number 2, which she did not do, would have had a particular outcome when she uncovered coin 1 instead. These 3 different possibilities, the choice of which coin to uncover, are really incompatible with one another. That's why the other coins disappeared. You have to do one of the 3, and then you can never really speak about what would have happened if you had made another choice instead. Another lesson is that in this case, the randomness, the fact that we're speaking in terms of probabilities, does not arise as probabilities normally do from our ignorance about the complete situation. In fact, the randomness, the probability assignments to the different outcomes, really is something intrinsic about the state of the coins. Even if you knew exactly what Donald did to prepare the coin set, you still wouldn't be able to predict the outcome when you uncovered one of the coins, whether it would be heads or tails. Now, one thing I should emphasize, and sometimes it's easy to get confused about this, is that although these are unusual correlations between Alice's lab and Bob's lab, different than the ones we would see if these were ordinary classical coins, they don't allow Alice and Bob to instantaneously communicate with one another faster than a light signal could travel between Alice's lab and Bob's lab, because no matter what Alice does in her lab, if Bob uncovers one of his coins, he's going to find heads or tails with probability 1/2, and that's not going to tell him anything about what Alice did in her lab. The experiment really has to do with them uncovering their coins and then speaking after the fact about how their outcomes were correlated. Okay? So people can actually do this type of experiment. You don't really do it with coins. You do it with, say, atoms or photons, particles of light, or you can do it with spins of electrons. Actually, people have been doing experiments similar to this one since the 1970s and finding repeatedly that Bell's inequality can be violated. And in fact, only quite recently have these experiments become more convincing than they were previously. One thing people used to worry about, say, if you do the experiment with photons, so the 3 coins correspond to 3 different ways of looking at the photon. I'll say more about that in a minute. But photon detectors sometimes fail to fire even when there's a photon there, so you have to worry about the imperfect efficiency of observing whether you have heads or tails when you uncover the coin. And then you also have to worry about whether it might have been possible for a light signal to travel from Bob's lab to Alice's lab if Bob uncovers his coin first and then Alice later. You want to make sure those are really separated events, so there's no way for information about what Bob did to travel over to Pasadena. And so we call that the causality loophole. And in experiments done for the first time in 2015, these 2 loopholes were simultaneously closed by doing very high efficiency measurements on Alice's system and Bob's system, sufficiently far apart that the time to do the measurement was very short compared to the light travel time between the 2 laboratories. It's been done when they're about 1 kilometer apart using atoms or spins, which can be measured with extremely high efficiency. There's another thing that people sometimes worry about, sometimes called the free will loophole. And what that means is, well, do we really know that Alice and Bob have the freedom to decide which coin to uncover, or is there something that determines their choice as well as what they find when they uncover the coins. This is something that you can't really rule out with logic. It's possible that Alice and Bob that the whole game is rigged, and Alice doesn't have the choice of what to measure each time another pair of coin boxes is presented to them. But people have gone to rather extreme lengths to make that seem less likely. Experiments have been done in which what choice Alice makes in her lab is determined by the fluctuations in the starlight from a star in that direction on the sky, hundreds of light years away. And Bob makes his choice based on fluctuations of starlight hundreds of light years away in an opposite direction on the sky. And so if you believe that somehow the game is rigged, it has to be rigged to the extent that those two stars are conspiring with one another. Okay, so now let's try to go in a little deeper and understand how this could work. And now we have to talk about the quantum rules for calculating these things. And we have to use a concept which is actually a rather difficult concept when first encountered. I know Caltech undergraduates have trouble with it, something called the tensor product. And it's the quantum rule for how to describe what happens when you put two quantum systems together. In this case, Alice's coin set and Bob's coin set. Now, I'm going to call what Alice has and what Bob has a qubit. It's like a bit in that you either get heads or tails when you look at the coin. But in the case of a qubit, you're supposed to think of those two possibilities as being represented by orthogonal unit vectors in some abstract Hilbert space. And the general state of the coin can be a vector pointing in an arbitrary direction, where heads and tails might correspond to, say, a unit vector along the x-axis and along the y-axis. Now, this idea of a tensor product, maybe the easiest way to describe it is if you have two bits and you put them together, there are four possibilities. If you represent the bits by 0 and 1, it can be 0, 0, 0, 1, 1, 0, or 1, 1. But in the case of putting two qubits together, you're supposed to think of those four possibilities as orthogonal vectors in some four-dimensional Hilbert space. And the general state can be any combination of those four orthogonal directions, any vector in that four-dimensional space. So this is what Donald keeps doing. He keeps preparing this state. Instead of representing it by 0 and 1, I called it EX and EY to emphasize that you can think of these as orthogonal directions in a two-dimensional space. And so this would correspond to the bit state. There are two bits, 0, 1, and this to 1, 0. But I'm calling them EX tensor EY and EY tensor EX. And this is a particular combination of those basis vectors in this four-dimensional space. That's what Donald keeps preparing and sending to Alice, who has access to the first vector, and Bob, who has access to the second one. And you can see how these are correlated with one another. I've actually rigged things up so that if Alice tries to uncover coin number 1, she's asking, does the vector point in the EX direction? And if it does, then she says she has heads. She has heads, and if it points in the orthogonal direction, that corresponds to tails. And it's similar for Bob, except that I've flipped things around. So for him, the Y direction is when his coin comes up tails, and the X direction is when it comes up heads. And the state has that perfect correlation we talked about when they both uncover coin number 1. If Alice has heads, then Bob is sure to have heads, and if Alice has tails, Bob is sure to have tails. But I've also put in this funny minus sign here and combining together these basis vectors, and that makes this state anti-symmetric when you interchange the two vectors, Alice's and Bob's. And that has the interesting consequence that if Alice and Bob are both looking for the component of a vector in the same direction, the inner product of their pair of vectors with this combination is always going to be 0, because if they're looking at the same vector, then they have a symmetric state, and it won't have any inner product with it. It'll be orthogonal to this antisymmetric combination. And what that amounts to is that when they uncover coin 2 and coin 3, what are they doing? Well, they're looking at the component in this space for Alice's qubit along a direction which is rotated by 60 degrees. This component is going to correspond to Alice's heads, and the orthogonal vector to Alice's tails under coin number 2. And coin number 3, yet another direction, corresponds to heads, rotated by 120 degrees with respect to the initial direction corresponding to coin 1. And it's the same for Bob. His coins 1, 2, and 3 correspond to looking for the component of that vector along these 3 directions in this 2-dimensional space. So they're perfectly correlated when they both are uncovering the same coin. That becomes the statement that Bob's direction and Alice's direction are orthogonal in all 3 cases. But the interesting experiment that Alice and Bob did was Alice, let's say, measured her, or maybe Bob did coin number 2. And so then we know if Alice had also done coin number 2, she would have been looking at a vector which points in this direction, just because 1/2 is the cosine of 60 degrees, square root of 3 over 2 is the sine of 60 degrees. But instead, she looks at coin number 1, and so she's trying to find the component of this vector in the direction which is EX. That corresponds to heads if she looks at coin number 1. And then when you take the inner product of the 2, you get this 1/2. Now, the rules of quantum mechanics say that you have to square that inner product. And the reason we square it is we want the probabilities to sum to 1. And we know we can use the Pythagorean theorem to tell us that the squares of the components of a vector along all its components will add up to 1. And then when you wind up squaring the 1/2, that's where the 1/4 came from. Okay, so what we saw is that when Bob sees heads on coin number 2, Alice is going to see heads for coin number 1 with probability 1/4. And I rigged it up so that everything's so symmetrical that it'll be the same for any pair of coins that are uncovered and for when they both find tails or when they both find heads. Okay? So there are rules which we can use to easily calculate in agreement with what Alice and Bob found in the experiment. Those are the quantum rules. And the point of Bell's inequality is that these are just different rules, that you can't understand the experiment in terms of our usual classical notion of correlation or the interpretation of probability as reflecting our ignorance. How am I doing on time?
12 minutes still though.
I got 12 minutes left.
Still
Okay.
5 minutes more.
Okay. So if we want to have, and this, I guess I didn't say the words, that was an entangled state. In fact, we call it a Bell pair because it's what's made to order to violate Bell's inequality of these 2 qubits. And they're sort of inseparable in a way that we can't understand in terms of classical reasoning. And if you want to entangle, you can't use ordinary bits. You have to use qubits. And there are lots of ways of realizing a qubit in the laboratory in different physical systems. A qubit can be encoded in a single photon, say in whether its polarization is horizontal or vertical, the direction in which its electric field is oscillating. That can be a qubit. Or the spin of an electron, the direction of the magnetic field of an elementary particle like an electron can be either up or down along an axis, and that can be a qubit. Or the state of an atom, which could be either in its ground state or some excited state, that can be a qubit too. And those are all very remarkable encodings because the information is carried by this single particle system, a tiny little object, and yet we've learned how to control such objects quite accurately, so we can do precise experiments with those single quantum systems. But it's also possible to have more complex encodings. For example, in an electrical circuit at very low temperature where it becomes superconducting, so it can conduct electricity without any resistance, we can think of the two states of a qubit as persistent current in a wire circulating either clockwise or counterclockwise around the current loop. And that's also a remarkable encoding because it involves the collective motion of billions of electrons, and yet for information processing purposes it behaves as though it were a single atom or a single photon. Now, so why is this entanglement so interesting? Well, it's cool, right? Don't you think it's cool? But it's more than that. Why is it such a big deal? Well, to appreciate why it's a big deal, we should think about states with many qubits. Okay? And remember, if I have n bits, there are going to be 2 to the n possibilities for a bit string, because each one of the bits is either 0 or 1. But now in the case of putting together n qubits, we should think of those as the basis vectors in some really, really large space, which has 2 to the n dimensions. And if you wanted to write down a complete description of a quantum state, you would have to write down a vector in that huge space. Okay? So for just a few hundred qubits, like 300, the number of numbers you would have to write down, the number of dimensions in that vector space, is larger than the number of atoms in the visible universe. It'll never be possible to write that description down. Why would you want to write it down? Because it encodes all the correlations among the qubits in some particular quantum state. So even in the classical case, you have a vast number of possibilities, 2 to the n if you have 300 bits. But for any one of those possibilities, it can be written down very succinctly, right? It's just a string of 300s, zeros and ones. But for one particular completely known quantum state of 300 qubits, the description is vastly complex and just impossible to write down in classical language. And the lesson from that is something that we believe and have a lot of evidence for, but can't really prove from first principles, which is that it's not possible to simulate with a classical computer what a system of many qubits is doing by any efficient algorithm. Okay? So that means we should be able to build systems of qubits that can do things that we'd never be able to do with ordinary digital technology. And I would say this is the most interesting thing to me that's ever been said about the difference between classical and quantum. That classical systems are not capable, in general, of simulating what quantum systems do. So that means if you think about solving computational problems, there's an interesting classification. We think there are problems which are hard to solve with a classical computer, an ordinary digital computer, which doesn't take advantage of quantum effects, but they would be easy for a quantum computer if and when we succeed in building a powerful quantum computer. So of course it's interesting to understand what are the problems in this class, and we've learned a lot of things about that in the last 25 years. But I think for a physicist or a chemist, there's kind of a natural place to look for hard problems. Some years ago, 2 great physicists, Laughlin and Pines, made the point that we already have what you could call a theory of everything that matters in everyday life, a theory in physics that underlies all of chemistry and biology and geophysics and beyond. It's just the theory of the quantum mechanical interactions among electrons and atomic nuclei interacting electromagnetically in matter. It's described by the Schrödinger equation. We know very well that's the right equation, but in many situations it's just way too hard to solve. In fact, Laughlin and Pines went so far as to say, no computer existing or that will ever exist can break this barrier because it is a catastrophe of dimension. They meant that we can't even write down a classical description of a big quantum system. And they noted that, ironically, we've succeeded in reducing all of ordinary physical behavior to a simple, correct theory of everything, only to discover it has revealed exactly nothing about many things of great importance. And what they had in mind for things of importance are situations where quantum entanglement has an important role. We don't know how to describe that in any succinct or efficient classical way. Now, it happens that about 20 years before Laughlin and Pines made this statement, the physicist Richard Feynman had articulated a rebuttal when he imagined a quantum computer, a computer that operates according to quantum principles. He said nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. But for a physicist like Feynman or Laughlin and Pines, why is that interesting? It's because we think that a quantum computer should be able to simulate efficiently anything that can happen in nature. Now, we don't think that's true for ordinary digital computers because they can't simulate highly entangled systems of many particles. But that means with a quantum computer, we should be able to go more deeply into the properties of complex molecules and exotic materials, and also explore fundamental physics in new ways, for example, by simulating high-energy collisions of elementary particles, or the quantum behavior of a black hole, or what happens in the early universe right after the Big Bang. But in fairness to Laughlin and Pines, Feynman made this statement almost 40 years ago. He called for the building of quantum computers. Here we are 40 years ago. We're just getting to the point where these quantum devices are capable of doing interesting things, where I'm defining interesting as a task performed by a quantum computer that we couldn't do with a digital computer. So why is it taking so long? It's because building a quantum computer is extremely hard. It's hard because we want a quantum platform suitable for computing to meet some criteria which are nearly incompatible with one another. We want the qubits to be able to interact strongly with one another because that's how we're going to process the information that they're encoding. But we don't want the qubits to interact with the outside world, with the environment. And that's because quantum states are extremely fragile, that if you look at a quantum state, you'll damage it in some uncontrolled way. And you don't want anything in the environment to quote-unquote be looking at the quantum system. So you have to keep it nearly perfectly isolated from the outside world. But you want to be able to control the quantum computer from the outside world, to tell it what to do, and finally, at the end of a computation, to read out a result. And it's very hard to build a quantum platform that simultaneously meets all these desiderata. So it's taken a couple of decades of improvements in the design of qubits, in control protocols, in fabrication materials, to get as far as we have. So how far have we gotten? How am I doing now? About 5 minutes?
8 minutes altogether.
Okay. So I thought I'd tell you a little bit about a recent development which you may have heard about because it got a splash of publicity when a scientific paper appeared in Nature a couple of months ago. And this refers to an experiment that was done in Santa Barbara, just a couple of miles from here, in a laboratory operated by Google and led by Jean Martinez, who had been a professor of physics here at UCSB, in which they proclaimed that they had achieved what was called quantum supremacy. So the idea of quantum supremacy is to show that a quantum device is really doing something that would be too hard for any digital computer to do, even the most powerful in the world that we have today, in any reasonable amount of time. So what did they actually do? They built a machine, they call it Sycamore, which has 53 working qubits. So remember, that means its quantum state lives in a space of extremely high dimension, 2 to the 53. And that makes it hard to simulate on a classical computer. It has a layout in 2 dimensions like this. All of the gray crosses are the qubits, and the blue squares are the couplers between the qubits, all of which are controlled from the outside by microwave pulses. And we can turn the coupling between neighboring qubits on and off in order to perform an entangling 2-qubit operation on that particular pair of qubits. And we can put many such operations together in a circuit to do some kind of quantum computation. And a notable technical advance that this group achieved is they made these couplers very good in the sense that they can turn off the coupling very strongly, turn it on and off quickly to do a gate that's pretty fast, at least by the standards of quantum computing. So first of all, it's significant that it's a fully programmable quantum computer that they built. In principle, you can do any quantum computation on those 53 qubits by putting together the gates that they can perform in the right way. And they were able to show that when all the qubits are simultaneously undergoing operations, there's an error rate per 2-qubit gate, which is below 1%, about 0.6%. So that means if you did 1,000 operations, all but 6 would be pretty good, but 6 out of 1,000 would be kind of lousy. So that's a pretty high error rate, certainly compared to our digital classical technology, which has a negligible error rate. But for quantum computing, that's pretty state-of-the-art. An error rate per gate less than 1%. And they were able to put together circuits where they did 20 layers of these 2-qubit entangling gates with single qubit operations in between, and then read out the results at the end by measuring all the qubits. And then we could ask the question, first of all, is the noise so bad that they're just outputting junk so that there's no significant signal to noise? And we could also ask the question, if we tried to simulate what that device is doing, how hard a simulation would that be on a digital computer? And well, through some methods which I won't explain in detail, for computations which were not the biggest ones that they did, they were able to verify with a heavy-duty classical computation on a supercomputer that their quantum computer was really performing the way that it should and getting the right answer. Now, to get the right answer, they actually had to run the computation millions of times to get statistically significant results because the circuit was so noisy, but that wasn't really so hard for them to do. And because this is a very complex circuit without any special structure that can be easily exploited in a classical simulation of what the quantum computer is doing, they argued that for the most complex computation that they performed, that if you tried to simulate it with a classical computer, it would take thousands of years. That has been questioned, whether there are better methods of doing the classical simulation than what they did. But they were able to run their computation millions of times in just a couple of minutes, whereas I don't think there's any disagreement that if the world's most powerful supercomputer were trying to simulate it, it would take days at the least and probably much longer than that. So the quantum computer really does have a big advantage over the classical one. I called it Quantum David versus Classical Goliath because a supercomputer that they use for the simulations is Summit at Oak Ridge Laboratory in Tennessee, and it covers 2 basketball courts, and it uses, like 10 megawatts of power. But the Google group just has this little chip and a dilution refrigerator. It's really like a tabletop experiment. So that's David beating Goliath. So what's significant about this? Well, it's a programmable computer, which in principle you could use to do any computation with the size limited, however, by 2 things. One, that they only have 53 qubits, and secondly, that it's noisy enough so there's a limit to how many layers of gates they can do without the noise overwhelming the signal, so they just get a useless result. But it's an impressive achievement in experimental physics, and I think a testament to the ongoing progress in quantum technology that it worked as well as it did. And this is now perhaps the best experimental evidence that we have directly indicating that in the quantum world we have access to extravagant computational resources which we can't match with ordinary digital computers. That's not really a surprise, but I think it's a milestone which is worthy of note. What we're finding out is that building a quantum computer is really, really hard, and we still are on a long road which is going to take a while, but it's not ridiculously hard. We can make progress and are continuing to do so and can expect further progress in the future. And there are other places you can read about reactions to this development, including a column I wrote in Quantum Magazine that appeared in October. So I thought we should have a word for this new era which is starting to dawn. So I made up a word which kind of caught on. It's NISQ, N-I-S-Q. it stands for noisy intermediate scale quantum. And the intermediate scale is supposed to emphasize that with the technology we now have and are continuing to develop, we can already do computations which are just too hard to simulate with any digital computer. And that means 50 qubits and above is more or less in that intermediate scale regime, which we've now broken into. And the noisy emphasizes that the noise is a real limitation on the computational power of the current technology. It limits how long a computation we can do. Now, for physicists, it's an exciting time because this NISQ technology means we can explore the physics of many interacting particles in highly entangled states in a regime which has never been experimentally accessible before. And there are great hopes that we can develop practical applications of the technology perhaps fairly soon. There's a lot of investment being made by technology companies, not just Google, but Microsoft, IBM, Amazon, Intel, and so on, and many startup companies that are developing quantum hardware and software. But we really don't know whether we'll see practical applications anytime very soon. We shouldn't think of NISQ as something that's going to change the world by itself as a technology. Really, it's a step towards more powerful quantum technologies of the future. I really am confident that there will be transformative effects of quantum computing on society in the decades ahead, but we really don't know at this stage how long it's going to take to get there. And I guess I'm about out of time. The last thing I was going to talk about is kind of connect with something that we'll hear about in Matt's talk. I thought this was a funny headline which appeared in Gizmodo recently, right after a workshop that we had at Google X, to talk about connections between quantum computing and gravitation. So is it possible, and I think maybe it is, that we can learn things about quantum gravity using these quantum platforms, maybe not in the next 10 years, but in the next couple of decades? And why would one be hopeful about something like that? It's because we've been learning that if we want to think about the quantum mechanics of space-time, you know, it's often said, and quite legitimately, that we'll never be able to explore quantum gravity in experiments, because where the quantum effects in space-time are important are at exceedingly short distances, and in order to explore those distances, we have to get to correspondingly very high energies, which we're not going to be able to do with any particle accelerator in the foreseeable future. But now we're starting to think about space-time as something that's emergent from some deeper description of quantum reality, and that really it's quantum entanglement which in some sense is responsible for the emergence of space-time and for, if you like, holding space-time together. And so if that's really true, then it should be the case that we can get insights into how that works by studying very highly entangled systems in laboratory experiments. In a place like UCSB, in an experiment on a tabletop, by making very highly entangled systems in a controlled way, we should be able, in a sense, to create a universe that didn't exist before and study its properties. And I don't know for sure whether that prophecy will come true anytime in the near future, but I think we can say with high confidence that many exciting surprises await us as we explore the entanglement frontier. Well, thanks for listening.
Okay, we have about 10 minutes for questions. And please wait for the microphone so that it can be also recorded.
How does quantum noise compare with classical noise?
So the question is, how does quantum noise compare with classical noise? So when we speak of classical noise, what we usually have in mind is thermal noise at relatively high temperature. So what does relatively high temperature mean? Well, in the case of a quantum system, I didn't speak of these numbers, but in the case, let's say we're talking about the quantum computer, which I said is subject to noise operated by Google, which is really an electrical circuit at very low temperature. Well, the qubits actually have a frequency that you can think of. The qubit is just encoded in two different quantum states in this electrical circuit, a ground state and an excited state. And the splitting between them determines a frequency. And if the temperature were large compared to that frequency translated using Planck's constant into a temperature, then that would be like classical thermal noise in the device. So in fact, the experiments have to be done at extremely low temperature inside a dilution refrigerator at about 20 millikelvin. So the temperature will be small compared to the energy splitting between the two states of the qubit. And so that's the regime they operate in, where thermal noise isn't so much of a factor, but they have to worry about other things like fluctuations in the materials that they build the stuff out of. The superconducting circuits, the secret of what makes them good for qubits is something called a Josephson junction, which is a kind of nonlinear element you can put into an electrical circuit, and it's got materials in it which have excitations, like chemical bonds that can fluctuate between two different configurations, and that can be a source of noise, which is hard to control. That's one of the challenges, one of the types of quantum noise they have to worry about.
So with regards to your ground state and excited state, we know how to transition basically between those. You shine light at the appropriate frequency, the energy goes up in the electron.
Yeah.
How do they go about preparing the specific superpositions with the specific coefficients that you put up, the 1/2 and the square root of 3/2?
Yeah, well, so you're right. If I want to manipulate a qubit, which I can think of as two energy states of a quantum system with some precise splitting between them, then I can drive the system from the ground state to the excited state by pumping it at the right frequency. But actually, if you tune light to that splitting, what happens is that coherent oscillations occur between the ground state and the excited state. And by timing the pulse, how long those coherent oscillations occur, you can get any superposition of the two states that you like.
So it's those cross terms in the calculation have that certain frequency, but they can time it to that precision where they can stop it at a particular...
The 1-qubit gates are pretty good. Actually, I talked about the superconducting circuits because of this recent Google experiment, but as I had indicated in an earlier slide, there are a number of different technological approaches, one of which is to use individual atoms, which can be trapped using electromagnetic fields, as the qubits. And in the atoms that they use for that purpose are atoms that are also used to make some of the world's most precise clocks. And so they can be controlled with beautiful precision. The single qubit gates have precision which is better than error rates which are below 10 to the minus 4 for those atomic qubits. It's the 2-qubit gates that are hard because you have to have some controlled interaction between two qubits, between two atoms, or between two of these electrical circuit components. And that's the current limitation on the technology.
There was one question somewhere here.
Oh.
Hi, just to clarify, you spoke about the difficulties with classical computing as a catastrophe of dimensions,
Yeah.
But you also mentioned that there's no algorithm or program in order to do these calculations in dimensions.
Mm-hmm.
Is it just that you can't develop these programs, like in Fortran, like you can do lots of dimensions? Can you not develop the program, or can you not wait years for the results? Is it just the time, or is it that it's not possible to even do it? in
So,
a classical
yeah, okay.
computer.
So the question is, what really is
The
causing this
limitation.
limitation
Yeah.
on simulating a quantum system with a classical one? And it's really, the right way to think about it is how the hardness of doing the simulation scales with the size of the quantum system that you're trying to study. And so the catastrophe of dimension is that if you increase the number of qubits, now the quantum states are living in this vector space of higher and higher dimension, which is becoming very extravagantly large. And as far as we know, after decades of effort by physicists and chemists to develop the best possible simulations of a many-qubit system, for many problems, the runtime of doing the simulation grows exponentially with the number of qubits because of that growth of the dimension of the phase space. And so the limitation really is on how large a system you can simulate. 10 qubits, pretty easy. 20 qubits, you can do it. 30 qubits, it's starting to get challenging. 50 qubits, it's, essentially, it's getting out of reach. And so it's really, we'd like to be able to study larger systems, and what we're now getting to the point where we can make them and control them precisely in the lab, and they're big enough that the classical methods just fail in any reasonable amount of time. If you were willing to wait 10,000 years,
I guess that's
would
what
be
I
able
was
to get
asking.
results.
We can do the calculations, but it takes years.
You can do them, it just takes too long.
Okay.
Yeah,
Great.
that was a good, more succinct answer.
You used the phrase highly entangled systems a couple of times. So would that mean 50 qubits would define a highly entangled system?
Well, it doesn't have to be, of course. It's possible to have a state of 50 qubits which is not entangled at all. They could all be, heads along some axis. And of course, that would be as easy to describe as a classical bit string. So it's when they interact with one another and really start to explore this very big vector space that I would call it highly entangled. And that's when it becomes hard to simulate. Yeah.
Thank you.
One more question out here. Give me this. Oh, sorry, go ahead.
So my question goes back to the fundamental idea of how can you possibly read the quantum system, get information out without changing that quantum system? I still don't get how that has been almost solved.
So the question is, how is it that you can read out a quantum state without disturbing it?
Exactly.
You can't.
Okay.
When you read it out, you disturb it.
So then how?
So when we do a quantum computation, normally, this isn't always the case, but in many cases, you don't actually make a measurement until the very end. Until then, you're performing coherent manipulation of the qubits. What do those words mean? Well, it means we're doing things like discussed earlier, like you can tune, let's say it's an atom in a trap, laser to a particular frequency and leave it on for a certain amount of time. But you can do that without actually reading out the state of the atom. It'll be in some superposition of ground and excited, and it might be correlated with the state of some other atom. And we know how to manipulate the state without reading it out, without blowing up information about the state to the classical world, which if we did it, would indeed destroy the quantum state. And that wouldn't be the right way to do a quantum computation.
But then at the end, when you read it, don't you ruin anything that's there?
Well, yeah, but hopefully you're getting the answer at that point. Okay. So in the end, the quantum, it's an algorithm, and in the end, the answer is classical. So you can print it out on a piece of paper and publish it in a journal. And that result is the outcome of some measurement you do at the very end of these many steps of careful manipulation of the quantum state.
How will you know when the computing is actually done? Is there the possibility that there's no way to tell that it's actually gotten to the conclusion yet?
Well, So usually we have algorithms in mind which are intended to answer some particular question. So if I'm simulating some quantum system, maybe I'm interested in simulating a chemical reaction, and I'd like to know the probability that some particular reaction occurs. And so if I could carry out this algorithm without any errors, then it's designed to give me the answer to that question. But actually, what you're asking is very on target, because it's hard to check that the quantum computer is giving the right answer. There are some problems that a quantum computer that can solve that we don't think can be easily solved with digital computers, where we can check the answer. The most famous example of this is the problem of finding the prime factors of some large composite number. We believe that's a very hard problem for ordinary digital computers. Why do we think that? Because really smart people have been trying to figure out better ways to factor numbers, and still the best algorithms that they have a very bad scaling with the number of digits and the number to be factored. We know that there's an algorithm we can run that will solve that problem efficiently on a quantum computer if it's a sufficiently large one. And then once you have the answer, you can check it, because if you have the factors, you can multiply them together and see if they really give you the composite number. But that's not always the case. So like this question about the probability of some chemical reaction occurring, unless I do an experiment in the laboratory, I don't have a good way of checking it classically. And this is one of the issues, which is it's a goal of current research to come up with better ways of checking that a quantum computer is giving the right answer. And I don't think we have completely satisfactory ways of doing that now, though we're making progress on that.
Okay, let me take one more question, and then we can have further discussion in the break.
Could you comment on, I read somewhere that the problem that was solved with the Google computer was very strange, and no one would ever want to solve that problem. Could you comment on what was the problem that the quantum computer solved?
Yeah. So, well, I indeed agree with the statement. Well, maybe you could call it strange. I certainly agree it wasn't particularly useful. Well, there are some thoughts about how you can do something useful with this type of calculation. But really what they did is they just kind of threw together a bunch of gates in a circuit, and then in the end, they measured all the qubits. And so there are many possible outcomes for that final measurement. So it's not like you get one particular answer in every run of the experiment. Instead, you're sampling from some distribution of possible answers. And so they do that millions of times, and they try to get some useful sample from that distribution to characterize that distribution in some way. That's something that the classical computer can also do, and you can check whether the distribution that the classical computer predicts is compatible with the one that the quantum computer seems to be sampling from. At least you can do that before the computation gets to be of unmanageable size. And that's the kind of thing they were doing. So why would they do that? They do it because that type of computation has really no structure that would give the classical computer some leverage, some advantage in doing the simulation more efficiently. You just kind of have to do it by brute force, and that turns out to be very hard. There may be some computations you can run on a quantum computer actually are easy to simulate classically, and they wanted to find one that was as hard as possible for the classical computer within the limits of their current technology, the number of qubits they have, and the error rate. And so it's not a particularly interesting computation. I regard it instead as a test of the hardware showing that it's performing well enough to do something that digital computers can't currently do. And now the challenge is to turn that into a more useful application, which people will be trying to do in the next few years.
Well, how many qubits would you need to factor numbers that cannot be factored now?
Well, so suppose you wanted, this is actually an interesting question at several levels. So we use the difficulty of factoring as the basis for the security of the public key crypto systems that protect our privacy, say when you send your credit card number over the internet. And as that protocol is typically used today, you'd be able to break it if you could factor a number which is 2048 bits long. To break that protocol using a quantum computer, if it operated perfectly, a few thousand, 6,000 qubits would be enough. Okay? Of course, you have to run a long computation on those 6,000 qubits. The trouble is that because it's such a long computation, you need a very low error rate per gate in order to get the right answer. And the error rate I was talking about, a little bit better than 1%, isn't nearly good enough. So our current idea about how to do that, because you'll need an error rate per gate, which is better than 1 part in a billion, is to use a kind of error correction protocol, which means you redundantly encode the computation in a way that protects against errors, and so the errors can be corrected. But that means a lot of overhead in the number of qubits. So if you had technology, if you had qubit technology, maybe a little bit better than what Google has now, and you wanted to put in enough redundancy in the computation to do the error correction, even though the number of ideal qubits you need is just 6,000 or something like that, the number of physical qubits you would need would be in the millions. So that seems, unless we improve the qubit technology a lot, maybe with some completely different approach, that's probably a ways off, because we're at 53 qubits now.
Okay, so there are still many more questions, but let's take them out to the refreshments, and we'll adjourn at 10:50 in half an hour. So let's thank John again.
Thanks.